In this video, we're going to give a brief overview of the first three sections of Chapter 11 on sequences and series. I highly suggest watching this video at least 3 times, if not more. There are a lot of interconnected ideas, and I think the more times you watch this, the more things will make sense. One of the key things to talk about is the difference between sequences and series. A sequence is a list of numbers in a specified order, and each individual number is called a term. So here's some ways of writing down a sequence. I've in fact written the same sequence in 2 different ways for the first 2 points here. So if you have a nice formula for the nth term like this, 3 times n, that's great, and this is a nice quick way of writing this. But if you want to write out what this means, well, the first term is 3, the second term is 6, the third term is 9, the fourth term, or a sub 4, is 3 times 4, which is 12, and so on and so forth. And here's sort of a generic way. These are generic ways of writing a sequence. Of course, you could be talking about this sequence, but when you talk about a theorem or a test and a sequence comes up, the sequence has to be written generically like this. You can't write 3n inside a generic formula box inside the book, right? You have to just talk about a sequence generically. But that an you're talking about could be this 3n. In contrast, a series is adding up a whole bunch of numbers, and each individual number is again still called a term like it was over here. So you have a list of numbers, you have a sum of numbers, and here are some ways of writing down series. So here's some series, add up numbers of the form 1 over 3 to the nth power, and here's the same series written just kind of in a longhand notation. So these 2 series are the same thing. One of the terms happens to be 1 over 27. That happens to be the third term. And here are generic ways of writing down series. So again, if you have a specific series in mind, maybe your a sub n is this 1 over 3 to the n. You're just kind of matching up pieces in the formula. That's fine. But again, when you go to a test or something, the book's tests can't mention a specific series inside the test. So they'll write something like this, or write something like this. The idea is that the starting n doesn't matter, and the infinity up here is assumed. The key thing to do is to not confuse a sequence for a series or vice versa, and this comes not only just as far as being able to identify the two, but the whole point is that you have to use completely different techniques for sequences than you do for series. And if you use techniques for sequences on series, well, that gets you nowhere, and vice versa. So let's kind of overview the different techniques which are used. Different techniques used for sequences and for series. And that I don't think this slide is going to make a whole lot of sense unless you go through some of the details, maybe watch the video a couple times really for this slide to make sense. But I wanted to put this early on to really hammer home the point that you should not confuse sequences for series. So here are some techniques for sequences. One, you can use a precise definition which talks about epsilon and n. This is a very tedious task, and if at all possible, you should try to avoid using this technique, but sometimes you can't avoid that. You have L'Hopital's rule, you've got the squeeze theorem, you've got some basic limit laws like addition laws and so on. I'm sure I'm missing something in this list, but the reason that we only spent 1 section in the book is because you're basically using all the techniques you've used for functions. So when you study limit of f of x as x approaches infinity, that's really the same stuff as studying limit of a sub n as n approaches infinity. Just a sub n now is f of x, and the x is an n, and so all of the techniques you've used way in the past for limits at infinity for functions, all of those techniques come back, and that's what you use. In contrast, for series, now this is all new stuff, right? The ideas over here, you've used this all for functions before, but this is all new. You can try to directly show that the sequence S sub n converges or diverges for that matter, but when you would do this is often when you have a telescoping series and you can write a nice formula for S sub n. You could look at the geometric series test, the test for divergence, there's the integral test, there's a p-series test. There's this thing called the comparison test, but that's in section 4. And there's more tests, won't list them all here. But the key thing is most of these things, they're labeled with the word test, and a lot of these things back here are kind of familiar things from Calc 1. Okay. So one piece of confusion, I think, is that there are different phrases which we'll use which really mean the same thing. So let's start with a sequence. Instead of a sub n, I called it b sub n here, just to try to get you used to more notation. And here are several ways of saying the same thing. So you could say that the sequence Bn converges. Well, that's saying the same thing as the sequence Bn does not diverge, because converge and diverge are just simply opposites of each other. What does it mean for the sequence Bn to converge? Well, what this really means, okay, they all say the same thing. This means that the limit of Bn as n approaches infinity, that this limit exists. And again, what does this word exists here really mean? It means that the limit of Bn is a number. And to really clarify, this is a number means that infinity doesn't count, negative infinity doesn't count. You have to have a real number, something like 1,000,000 or -2 or 0 or pi or something like that, okay? So these four things, you have to keep this in mind, all say the same thing. And before we go through the same terminology for series, the point is that when you start with a series, there are two sequences to look at. One is the sequence of terms, and that sequence is just basically you remove the sigma. And so as an example, for this series right here, adding up the numbers of the form n minus 1 over 3n plus 1, the sequence of terms is just remove the sigma. It's these numbers. Okay, it's just a list of numbers now. And these two questions are going to be different. So does this series converge or diverge, and does this sequence over here converge or diverge? Well, these questions are different because it turns out that the answers are going to be different. So this series, we will see a little bit later, happens to diverge, and this sequence we'll see later, happens to converge. So don't confuse the two things, okay? One of these things converging does not automatically mean that the other does. One of these things converging does not automatically mean that the other does, okay? Lastly, for this series, there's a second sequence that we will need to look at, and that sequence is called the sequence of partial sums. We're not fully defining what that sequence is right here. You've seen some examples, so take a look. In class, for instance, we looked at this series, so sorry, the sigma is off to the side and the n minus 1 is off to the side. Normally this is underneath, but I'm running out of room. But the sum of the numbers of the form 1 over 2 to the n, we actually painstakingly computed a nice formula for the nth term of the sequence of partial sums and got 2 to the n minus 1, all divided by 2 to the... Alright, start with a series, sum, doesn't matter what n starts at, but sum of the numbers a sub n, and we'll use s sub n to denote the sequence of partial sums. And then this is not equivalent to the stuff we saw earlier, okay, but here's some pieces of terminology, here's some bullets that will say the same thing. One is you could say that the series converges, and that's really saying the same thing as the sequence. Get that? Let's get that right. Okay, so the series converges means exactly the same thing as the sequence converges. But these are not the same. See, it's not an and an here. It's an and sn. So for the series, look at sn, the sequence of partial sums. If the sequence of partial sums converges, that's the same as saying the series converges, series an converges, and the sum of numbers of the form an converges is the same as saying the sequence of partial sums for an, which is called sn, converges. And then here, just tying this to the earlier terminology we've seen, what did it mean for a sequence Sn to converge? That means that this limit exists or that this limit is a number. Whatever number that you get, that's what this series is. Okay, this series adds up, this sum adds up to a specific number, and that number has been called S in the book, and that's whatever this limit is. Alright, so the test for divergence talks about both a series and a sequence. Here's a summary of that test. It says start with the series sum of numbers an, and now you're going to analyze a sequence. Okay, so look, we're already talking about a series and a sequence. Keep the two things apart. A series is studied using series techniques. A sequence is studied using sequence techniques. And here's what happens. You look at that sequence, and if the sequence diverges, then the series happens to diverge. Okay, this is just something special due to the test for divergence. And if the sequence an converges, and if that limit is any number that is not 0, then the series here diverges. Again, we have one series, one sequence, and we're talking about both of them at the same time. Just note that if this sequence here an does converge, but the limit happens to be 0 instead of non-zero, then you get no information at all. You can't use the test for divergence, you got nothing. And let me kind of point your attention to this. Here you have to analyze the sequence A sub n, and be sure when you study this sequence that you use sequence techniques. Using series tests, things like the geometric series test or using the integral test on this A sub n is not going to work, right? You have to study the sequence here using things like L'Hopital's rule or the squeeze theorem or other sequence techniques that we saw on that techniques slide. So here's the key point. The test for divergence allows you to sometimes, and I say sometimes because here you can say something and then in this case you can't. But what you get to do is you get to say something about a series by not really studying the series itself. What you're doing is you're studying the sequence. And so if the sequence does something right, you get to say something about the series. But the point is you encounter a series, and instead of, so that series you'll study with a series technique, and one of those is the test for divergence. But immediately, what do? Is you ditch the series because the test tells you to analyze this sequence, called the sequence of terms. Let's look at this on an example. If you add up numbers of the form n minus 1 over 3 to the n plus 1, is this going to converge or diverge? Keep in mind that this is a series due to the sigma, not a sequence, so you must use series techniques. If you use a sequence technique right away, you're going to get nothing. So you have to pick an appropriate series technique. Not every series technique is going to work. In this case, the one to pick really is going to be the test for divergence. The test for divergence immediately says to ditch the series, but to look at the sequence of terms. So here's the sequence of terms. This is the nice formula for the nth term. Basically, just ignore the sigma. Now that we're looking at a sequence here, though, you have to use sequence techniques. So study the limit of the sequence using sequence techniques, not series techniques. And the technique to study the limit of this, so the limit of this right here, is actually going to be L'Hopital's rule. So then you'll have limit of the constant of third, and that limit is just simply 1/3. Now we've finished studying this sequence right here, using sequence techniques, and now you can go back to what the test for divergence says. The test for divergence said that if this sequence of terms for the series, if the sequence of terms converge to a non-zero number, in this case 1/3, well, the test for divergence says that the series diverges. Okay, so the sequence here converged, but the series right here diverged. Here are some fallacies that often come up, and this will, if you do these kinds of things, you will really just kind of struggle through an exam. But if the sequence of terms has a limit of 0, then I repeat, the test for divergence gives you no information at all. So for example, if you look at the series, you add up numbers of the form 1 over n squared. The sequence of terms happens to just be 1 over n squared without the sigma. And this sequence has limit 0, right? This is 1 over growing stuff, so the limit of this is going to be 0. The test for divergence says nothing about this series. You have to move on to a different test in order to say something about this series. And the test that you need is not the test for divergence here. You need the integral test, or you need the p-series test. Also, you can waste a lot of time by trying to play too much with the sequence of partial sums. So if you could try to write out, S sub n, write out what's S1, what's S2, what's S3, just by adding the first 3 numbers, adding the first 4 numbers, and that's fine if you want to get a feel for what's going on. But if you cannot come up with a nice formula for the nth term, you should move on to another test. Studying the sequence of partial sums directly does not very often get you anywhere. You typically want to do this for telescoping series and for some other really special cases. But we know from the p-series test, or really from the integral test, that this series here and this series do different things. So this series happens to diverge because p is 0.9. Here this series happens to converge because p is 1.1. And let's suspend using for a second the p-series test or the integral test. But if you just looked at these two series individually and you wrote out the sequence of partial sums in each case, you wrote out Sn over here and you wrote out Sn over here, well, first of all, good luck trying to do this without a calculator. But let's suppose you even had a calculator with you. So you wrote out Sn over here, you wrote out what's S1, S2, S3. Here you add up the first 3 numbers, the first 4 numbers you add up. You wrote out what's S3, S4, and so on. You couldn't possibly conclude anything anyway. In both cases, Sn is going to be an increasing sequence. It just turns out that in this case, Sn is going to increase all the way on up and without bound and go to infinity. And in this case, Sn is going to actually approach a specific number. We don't know what number, but you can't just analyze Sn if you don't have a nice formula for the nth term of Sn.